the James Webb Space Telescope JWST peers deep into the cosmos, capturing light that has traveled for over 13 billion years. However, due to the universe's expansion, this light has stretched, shifting into the infrared spectrum. By observing the most distant galaxies, we are effectively looking back in time, nearly to the Big Bang. The vastness of the universe may seem incomprehensible, yet all of it originated from what is known as the singularity. Our current understanding of the Big Bang hypothesis suggests that the universe began as a dense and hot point, expanding rapidly to give rise to matter, energy, and fundamental forces. The JWST has already unveiled significant secrets regarding the birth and evolution of the cosmos, leaving scientists and astronomers astonished. Physicist Brian Cox has noted that these striking discoveries could potentially reshape our entire perception of the universe. The JWST, named after NASA Administrator James E. Webb, stands as a marvel of modern space exploration. It represents a monumental technological leap from its predecessor, the Hubble Space Telescope, and was developed through a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. Unlike Hubble, which primarily operates in the visible and ultraviolet spectrum, the JWST focuses on the infrared range, allowing it to see through cosmic dust and capture celestial objects that were previously hidden. Its massive 6.5 m primary mirror, composed of 18 hexagonal segments, dwarfs Hubble's mirror in size, making it the most powerful space observatory ever built. Positioned 1.5 million km from Earth at the second range point L2, the JWST maintains a stable orbit, ensuring an unobstructed and continuous view of the cosmos. Observing distant regions of the universe is akin to a form of time travel. As light from these celestial objects travels towards us, it undergoes redshift due to the universe's expansion, shifting from the visible spectrum to the infrared. This shift allows JWST to detect light from some of the earliest galaxies that formed in a universe, enabling scientists to study star formation, galaxy evolution, and exoplanet atmospheres in unprecedented detail. One of JWST's most groundbreaking discoveries is the identification of an enormous cluster of galaxies at the edge of the observable universe. This finding challenges some of the assumptions held within the Big Bang theory, forcing cosmologists to reassess key aspects of their models. Understanding how we arrived at this point requires revisiting the history of space exploration. Early civilizations such as the Greeks and Chinese laid the foundation for astronomy by carefully documenting the motion of celestial bodies. In the 17th century, Isaac Newton's laws of motion and gravity provided a theoretical framework for space travel. The early 20th century saw Edwin Hubble's revolutionary work in observational astronomy, where he demonstrated that distant nebulae were actually separate galaxies beyond the Milky Way. His observations led to the formulation of Hubble's law, which established that galaxies farther away from us are moving at higher speeds, providing compelling evidence for the expanding universe. The post-World War II era ushered in the space race with landmark achievements such as the Soviet Union's launch of Sputnik in 1957, Yuri Gagarin's historic orbital flight in 1961, and the Apollo 11 moon landing in 1969. The launch of the Hubble Space Telescope in 1990 marked another major milestone, providing breathtaking images and groundbreaking insights into the universe's structure and history. Hubble's discoveries, such as the famous pillars of creation in the Eagle Nebula and the Hubble Deep Field Image, fundamentally changed our understanding of the cosmos. It also contributed to the study of exoplanets, identifying water and organic molecules in their atmospheres, hinting at the possibility of habitable worlds beyond our solar system. The JWST was designed to build on the legacy of Hubble while addressing some of its limitations. Unlike Hubble, which struggles to penetrate cosmic dust and detect the faint infrared light from early galaxies, JWST's infrared capabilities allow it to peer deeper into space and further back in time. Its ability to observe celestial objects formed just a few 100 million years after the Big Bang is revolutionizing our knowledge of the universe's origins. These observations have uncovered an unexpected abundance of early galaxies, suggesting that galaxy formation occurred more rapidly and in a more complex manner than previously thought. Some of JWST's findings have raised intriguing questions about our current cosmological models. For instance, it has detected a larger number of massive galaxies in the early universe than expected, suggesting that the process of galaxy evolution might be more rapid than previously assumed. Additionally, some of these galaxies appear more mature than models had predicted, challenging conventional assumptions about the gradual formation of cosmic structures. Furthermore, the discovery of massive galactic clusters at extreme distances calls into question some of the assumptions regarding large-scale structure formation. The universe appears to have developed into an intricate and dense cosmic web much earlier than expected, hinting at previously unknown physical processes at play. One of the key tools JWST uses to investigate these mysteries is spectroscopy, a method that analyzes the light emitted or absorbed by celestial objects. Spectroscopic data provide insights into the chemical composition, temperature, density, and motion of cosmic bodies. Initial observations of early galaxies suggested a simple composition dominated by light elements like hydrogen and helium, in line with expectations. However, JWST's advanced spectroscopic analysis has detected unexpected variations, including heavier elements that challenge existing theories about the early universe's chemical makeup. This suggests that the formation and distribution of elements in the cosmos may be far more complex than previously thought. While JWST has revealed surprising discrepancies in some aspects of our cosmological models, it has also confirmed several foundational theories. For example, its measurements have validated the presence of key elements such as hydrogen, helium, carbon, oxygen, and nitrogen in distant celestial bodies, supporting theoretical predictions. These findings align with the widely accepted lambda cold dark matter lambda CDM model, which describes the universe as consisting of ordinary matter, dark matter, and dark energy. However, some discrepancies in JWST's observations have led scientists to reconsider alternative cosmological models. Several alternative theories have been proposed in response to the challenges posed by JWST's discoveries. The cold dark matter model suggests that most of the universe's matter consists of dark matter which does not interact with electromagnetic forces but influences cosmic structures through gravity. Another speculative theory is the semi-steady-state cosmology, which proposes that the universe undergoes continuous cycles of expansion and contraction rather than originating from a singular Big Bang. The mirror universe hypothesis posits the existence of a parallel universe with its own distinct physical laws, potentially offering alternative explanations for cosmic anomalies. Other ideas, such as the digital simulation hypothesis, suggest that universe itself may be a sophisticated simulation. Meanwhile, the multiverse hypothesis proposes that our universe is merely one of many, each with unique physical laws and properties. Despite the fascinating possibilities offered by these alternative theories, none have yet displaced the Big Bang theory as the prevailing model of cosmic evolution. Observations from JWST continue to align with the idea that the universe began with a singular, explosion-like event followed by rapid expansion. The presence of massive galactic structures at the edge of the observable universe suggests that gravitational forces were already shaping the cosmos in its earliest stages in accordance with Big Bang predictions. However, the inconsistencies and surprises uncovered by JWST highlight the need for continued investigation and refinement of our cosmological models. JWST has opened a new frontier in our exploration of the universe, providing glimpses into the earliest epochs of cosmic history. Its discoveries challenge established principles and push the boundaries of what we know about the formation and evolution of galaxies, stars, and planetary systems. With every new revelation, we are reminded that our understanding of the universe is still evolving. The telescope's findings have prompted scientists to rethink fundamental concepts, explore new theories, and refine existing models. As research continues, JWST's observations will undoubtedly shape the future of cosmology, shedding light on the mysteries of the cosmos and deepening our appreciation for the vast, intricate tapestry of the universe. The discoveries made by the James Webb Space Telescope, JWST, are already reshaping our understanding of the early universe, but they also have significant implications for other fields of astronomy. One of the most exciting areas of research involves exoplanets, planets that orbit stars outside our solar system. Scientists have long wondered whether some of these distant worlds might harbor conditions suitable for life. The JWST is helping to answer this question by analyzing the atmospheres of exoplanets, searching for signs of habitability and even potential biosignatures using a technique called transmission spectroscopy. The JWST observes starlight passing through an exoplanet's atmosphere during a transit. By studying how this light is absorbed at different wavelengths, astronomers can determine the chemical composition of the atmosphere. This has already led to the detection of water vapor, carbon dioxide, and methane on certain exoplanets. The presence of these molecules is particularly intriguing because they play a crucial role in planetary climates and could indicate the presence of processes similar to those found on Earth. One of the most promising targets for these investigations is the TRAPPIST-1 system, located about 40 light-years away in the constellation Aquarius. This system consists of 7 Earth-sized exoplanets, 3 of which orbit within the habitable zone, the region around a star where liquid water could exist on a planet's surface. Previous studies using the Hubble Space Telescope provided preliminary evidence of atmospheres around these planets, but the JWST's advanced infrared capabilities allow for much more detailed observations. If JWST detects oxygen, ozone, or other potential biosignatures, it would mark one of the most significant discoveries in the search for extraterrestrial life. The search for life beyond Earth extends beyond exoplanets. JWST is also studying objects within our own solar system, including the icy moons of Jupiter and Saturn. Moons like Europa and Enceladus are of particular interest because they contain vast subsurface oceans beneath their icy crusts. Observations from the Cassini spacecraft have already revealed that Enceladus emits plumes of water vapor into space, suggesting that hydrothermal activity might be occurring Beneath its surface, JWST has the potential to analyze the composition of these plumes, looking for complex organic molecules that could indicate the presence of life or prebiotic chemistry. JWST's ability to study the atmospheres of celestial bodies extends to our own solar system's outer planets as well. It has already provided new insights into the atmospheric compositions of Jupiter, Saturn, Uranus, and Neptune, detecting trace gases and studying cloud dynamics in unprecedented detail. These observations help scientists refine their models of planetary atmospheres and better understand the formation and evolution of gas giants. This knowledge is crucial because gas giants play an important role in shaping planetary systems, influencing the orbits and stability of smaller rocky planets. Beyond planetary science, JWST is also contributing to our understanding of stellar evolution. The birth, life, and death of stars have profound implications for the formation of galaxies, planetary systems, and even the fundamental elements that make up the universe. JWST's infrared capabilities allow it to peer deep into dense interstellar clouds where stars are forming. These regions, often obscured by dust and visible light, are now being observed in exquisite detail. The telescope has already captured breathtaking images of star-forming regions such as the Carina Nebula and the Tarantula Nebula, revealing intricate details of protostellar disks and jets. Another key area of study is the final stages of a star's life cycle. When massive stars reach the end of their existence, they explode in spectacular supernovae, dispersing heavy elements like carbon, oxygen, and iron into space. These elements are the building blocks of planets, moons, and even life itself. By studying supernova remnants, JWST provides valuable data on how these elements are distributed throughout the cosmos. One particularly interesting target is SN 1987A, a supernova that exploded in the Large Magellanic Cloud, a neighboring galaxy to the Milky Way. JWST's observations of the supernova are helping scientists understand the complex physics behind stellar explosions and the formation of neutron stars or black holes. One of the most enigmatic aspects of modern astrophysics is dark matter and dark energy. While dark matter is believed to make up roughly 27% of the universe's total mass energy content, it remains undetectable by conventional means because it does not emit or interact with light. However, its presence can be inferred through gravitational effects on galaxies and galaxy clusters. JWST is helping astronomers map the distribution of dark matter by studying the way its gravitational influence bends and magnifies light from distant galaxies in a phenomenon known as gravitational lensing. These observations provide crucial data for